you're going to want to rewatch this several times, I'm telling you. Not so much because of my excellence, but because of the excellence that is physics. So, anyway, what we're learning today is it's the backbone, it's the foundation, it's the fundamental stuff that we're going to use to really start studying motion. It turns out that if you go back to Newtonian mechanics, Isaac Newton's physics, right, in the late 1600s, 1680, I believe, but don't quote me on that. He published his big works, and the revolution with all that was, he said, if you know the conditions on an object, you know what it's going to do for eternity. It was called deterministic physics, right? You can figure out, if I know where something is and how fast it's moving and what its acceleration is, I know everything about it for the rest of eternity. Right? Pretty powerful ideas. And it turns out that in the early to mid-1900s, quantum physics came along and said, well, that's not entirely true. And throughout stuff like uncertainty and chaos theory gets in there and makes for some interesting exceptions. But there's a reason why it took us 200 years to figure out that Newton wasn't quite right about that determinism. Right? Because for basically everything that we're ever going to see in our lives, we do know everything. If we know the initial conditions, we can find out what's going to happen for the rest of it. So the stuff that I'm showing you here is enough to build airplanes and send humans to the moon and bring them back. The physics that we're doing here is pretty powerful. So let's take a look at it. All right, and we're going to start by realizing that these should be your tattoos. All right, so your homework assignment tonight is to go to your favorite local tattoo shop. And right next to the avocado, I want you to get these two equations that I'm going to give you today tattooed in prominence. The best option is to put it right here on your forearm, probably on the left forearm so that you can just always look down at it. You can do it there. If you're a big fan of the selfie, any of you guys take a lot of selfies, do a lot of Snapchatting, you can put it across your forehead. That way in every picture you've got the equation. Make sure you do it backwards so that you can read it in the picture. All right. Be a good look. Regardless, it must be made permanent on your body somehow so that even when you're old and wrinkly, you look down and, oh, yes, I remember that. It'll be good. So, let us begin. Your new tattoos. This is exciting. What I'm showing you works for all motion, as long as you have constant acceleration, which in the world we usually do. Or we can at least break it down to some time that we do. The old stuff, what we've been doing, still true. Right? It's not like I told you something that wasn't quite true. It is still true. It's just not always the most useful or the easiest way to solve problems. There's a more general way. It's kind of like when you first, in Algebra 2, when you first look at quadratics. First you factor them. And then you learn, well, some of them factoring doesn't work that well. So now we're going to teach you the quadratic formula, right? I'm showing you the quadratic formula of motion problems, if you will. And I want to start with an aircraft carrier. Because I think this is a way to build these equations where it will actually make sense. And they should. There's an element of common sense to them. So remember what we're trying to do. Given the initial conditions, we're trying to figure out where something will be at any time down the road. All right? So for this example, I'm going to build a base right here. Let's call this base Pearl Harbor. Because then we get to be in Hawaii, which is nice. And it's right next to the ocean. And then out in the ocean, we've got an aircraft carrier. Big old aircraft carrier. Right, there's the water around it. Don't laugh at me. And on the aircraft carrier, we've got an aircraft that can take off from the deck. And it's going to accelerate as it does. So, basically what we're trying to do is we're going to try and come up with an equation that tells us how far the aircraft is from the base at all times. All right? Now realize this is just one example. The equation that we come up will work for anything. Right? So that's why I'm trying to kind of come about it in this concrete sort of way so that it maybe actually makes a little bit of sense. There's three things that I need to worry about. three kind of factors that come into play here. The first one is pretty common sense. How far apart do they start? Right? Do you see how that's gonna come into play, right? How far from the base are you when the clock starts? And we're going to call that our initial position, which gets this little subscripted 0. We call it x aught. Fancy word for 0, right? But it means how far are you when time starts. So that's this distance right here. That's one thing you'd need to know if you were going to figure out how far away they were. You got to know how far you started, right? Another thing that you got to know is you got to know how fast the aircraft carrier was moving when the plane took off. Right? So we're going to call that v-aught, the initial velocity. And then the last thing that we're going to worry about, what else do we need to know? How fast is the plane accelerating off of that aircraft carrier? So that's the last one. So we also need to know what is the acceleration. If you know those three things, you know it all forever. So let's do that. Let's try to build the equation. It looks like this. First of all, and let me be clear about this, because this is something we always have to do when we do motion problems. I'm going to say the base is my reference point. In math, you call this the origin, right? It's where the two axes cross. This is our reference point or our origin. And I'm going to define anything going to the right is my positive x direction. Anything going to the left is negative. All right, that's going to be really important. So now let's build that equation, all right? Looks like this. X, and I'm going to do function notation. You guys cool with function notation? X as a function of time. Just makes it really clear that the position depends on time. Depends on three things. All right, well, the simplest one is I've got to start off, this whole equation needs to start this distance from where I began, right? So I'm going to start off by saying my position is equal to wherever I started. And now I just have to factor some stuff in. Let's factor in the constant velocity of the aircraft carrier. How would I do that? If I know that the aircraft carrier is going to be moving, what's an equation that tells me the distance it's traveled over time? We can do that, right? Remember that one? Distance is the average velocity times the time. Is the velocity of the carrier changing? It's constant, right? It's just going to move through the water. The acceleration comes from the plane. So instead of the average, what are we calling it? We're calling it the initial velocity, right? Does that make sense? No? Yeah? 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 Yeah. All right. So now, this is all good. Now we just need to figure out how do we account for the distance covered by this accelerating object. And the nice thing is, we already know this equation right here tells us where the aircraft carrier is going to be, doesn't it? So we just need to add in how far ahead of the aircraft carrier is the plane. Does that make sense? We're just trying to figure out how far ahead of the carrier is the plane. So what that means is we can imagine that this is sitting still, right? That now just for a moment, let's pretend that our reference point is sitting right here. We're just trying to find where the plane is after it accelerates. And for that, I think I need to do just a little bit of side work to get us to the answer. But follow this. It's not too bad. It's actually doing exactly what we've been doing in this chapter. If I know the acceleration, then all I need to do is I need to start with this equation where the distance traveled from the accelerator is the average velocity times the time. How do I find the average velocity for the airplane compared to the aircraft carrier? Average velocity, remember, is 1/2 the final velocity plus the initial velocity, right? This is the average velocity. That's an equation that we have, and then I'm just going to leave the time up there because it was already there. Now, remember I said we can compare it to the aircraft carrier. What's the initial velocity compared to the aircraft carrier? When you're sitting on the deck of the aircraft carrier about to take off, what's your initial velocity compared to it? It's 0, right? Compared to the carrier, you're not moving at all. So this goes bye-bye. So now we can simplify this, and it's just going to be 1/2 the final velocity times the time. Do we know yet? We don't know yet what the final velocity is, right? But if we know the acceleration, we can find it. Right? Because remember that the change in velocity is equal to the acceleration times the time? Right? I mean, that's what acceleration is. If you're accelerating at 9.8 or 10 meters per second, then after 1 second you're going 10, after 2 seconds you're going 20, 3 seconds you're going 30, right? So the velocity is just acceleration times the time. All I'm going to do is I'm going to go whoop, and I'm going to put that in here for my final velocity. So remember this was an equation for distance. I've got distance is equal to this 1/2 times AT, because AT is my final velocity, times t. Can I do one more set of algebra here? And distance is equal to 1/2 AT squared. Is that cool? And so without integration, I just found the distance of an accelerating object. Those of you guys who may have had calculus, that's kind of cool to see. So there it is. Anybody got chills right now? It's okay, you don't have to tell me. It'll be our little secret. This right here, though, this is, for most of you guys, the first tattoo of your life. Congratulations. Even if it's not the first, it's definitely the best. Write that down, put boxes around it. Of course, I'm kidding about the tattoos. But I'm not kidding when I say that this may be the most important equation we do all year. If you only remember one equation this year, you can make a good argument that this is it. We're going to use the heck out of it for the first 2 chapters, and then it'll keep coming back around afterwards, because it tells us the position of any object over time. Right, as long as we know the initial conditions, where it starts, how fast it started moving, and what the acceleration is. All right. Quickly, let's look at, I told you there were 2 equations today. This equation has a little brother. Whoops. If you're a calculus folk, you could take the derivative of this equation. Don't look too excited. If you're not a calculus folk, you can still come up with a little brother equation just by thinking about it. So what we want, the first one was an equation for the velocity, or I'm sorry, for the position. Tells us where it is. This one is going to tell us the speed. So if I want to know how fast something's moving, I need to know 2 things. Can you tell me one of them? What's one of them, Josh? Time will be a factor. This is going to be a function of t. That's good. What else do you need to know? Yeah, it looks like a banana. That's big, right? You got to know the acceleration. In fact, you multiply acceleration times the time, that tells you how much your speed increased or decreased, right? Anything else? You. Distance doesn't matter for velocity. Does that matter? How fast you started? Yeah, sure that matters. So this can be like the, I don't know, use it for like the decoration or the garnishing on your tattoo. This is good. We'll use it. It makes sense though, right? How fast you're moving is equal to the speed you started plus whatever the change is. And so there we go. Those two equations are basically going to be, there's a lot in them. Right? Enough that we can cram easily the next 5 or 6 weeks of this class into those equations. And have lots of fun doing it. So that's it. We're going to practice those today. The one thing I want to be clear of, because I've skipped over this in the past, is when we use these equations to solve problems, this one and the Big Brother equation, we've got to be really careful to specify axis and origin. We've got to say, what are we comparing it to? What's our reference point? And what direction is positive? Because if we don't do that, we make silly mistakes. Right? By far the most common mistakes come from not choosing an origin and not choosing an axis or saying which direction is positive. So this slide is just going to practice that. All right? Now, in general, and this isn't always true, in general, usually we say that up is positive and down is negative. Right? You could do it the other way, but it just makes sense, right? You think about math class, because math is where you learn the stuff that we use in here. In math class, that's usually how it works, right? If you were to draw your y-axis, it would look weird if somebody said, this is the positive y direction, right? Up is always positive, plus y. And it would look weird if somebody said, this is the positive x direction, right? There are times in here when we'll do that, because it makes the math easier. But usually, we're going to say up is positive and either forward or to the right is positive. Now, know this. This causes confusion too, but there's not much we can do about it. If I solve a problem using up as positive, and you solve the same problem using down as positive, we'll get the same answer, as long as we're both consistent the whole time. So do whatever you want. Sometimes one makes the calculations easier than the others. All right. Let's practice this, guys, because I've been talking a lot, trying to get you to the exciting stuff. I want you guys to try these first three. So here's a rocket blasting off, right? Just left the launch pad and it's taken off up in the air. Here is Serena Williams tossing up a tennis ball. This ball just left her hand, right? She's tossing it up. It just left her hand. She's going to smack it. And here's some poor fool about to die. I'd like you guys to go through and tell me, for the acceleration and for the velocity, positive or negative. There's no zeros up here. So remember we did this with graphs? We looked at graphs and we tried to decide positive or negative acceleration, positive or negative velocity. Do this for the pictures right now, please. Do it by yourselves, and then we'll talk about it in 1 or 2 minutes. Go. Before we start, let me warn you, there's 2 major misconceptions that we have with this. Number 1 is instead of velocity, it's easy to think speed. Right? The difference between speed and velocity is what? Direction matters, right? So let's look at this guy, because he shows that very, very well. As he falls, what's happening to his speed? Speed is increasing, right? You fall faster and faster and faster. So that must mean, that you have a positive acceleration, right? You don't. Right? That's thinking in terms of speed. if we think in terms of velocity, what's actually happening is you're going from a speed of, remember your speed's downward? So it's going from negative 10 to negative 20 to negative 30 to negative 40. Your velocity is decreasing, right? It's becoming more negative. So the acceleration here is actually going to be negative. You want a more conceptual way to think of that? I do. Acceleration, if we think ahead a chapter or two chapters, I think, acceleration is equal to force divided by mass. Have you seen that before? If the answer is no, don't tell me. You should have seen that before. So the acceleration is related closely to the force, right? So find the direction of the force on the object. If you're falling, the force is downward, right? That's in the negative direction, so the acceleration has to be negative. All right? Good. What about the velocity? What do you say for the velocity here, Zach? You say negative? Why? Okay. Yeah. Okay. Yeah, so up is positive. He ain't going up. So he ain't going positive. Right? That's one way to think about it. Zach, it sounds like, may have been thinking about the graph that he made. Right? When we did our motion graphs. He said it's getting closer, so the slope is down. Slope is the velocity, so it's negative. I don't know if that's what you were saying, but it's a connection we can make. What about Serena? The acceleration of the ball. What do you guys think? What did you say, Enrique? You put positive? Why? When she throws it up, it's getting higher. Good. It's moving upward. What do you think, Barrett? Positive?
But would it affect his, since it's not much gravity on it, doesn't it slow down as it goes?
Right. So here's where we maybe get into another misconception. I said, and I was careful to say this, I hope you heard it, she's just released the ball, right? The ball's not in her hand anymore. Once the ball leaves her hand, does the ball have any memory that she used to be pushing it up? No, and that's really important to realize. The ball has an upward velocity because inertia is carrying it upward. But the ball has no memory whatsoever that she used to be forcing it upward. What is the actual force on the ball? The only force on the ball is gravity, and gravity is pulling it down. So does that help? What direction is the acceleration? It's downward, and we said down is our negative. So we've got negative acceleration. Can I tell you guys a secret? I hate to give you shorthand, and maybe this exposes one of my weaknesses. I think it's a strength. I hate to give you guys shortcuts. I'd rather have you actually understand it. But anytime gravity is the only force acting on something, the acceleration must be negative. Right? Because gravity always pulls things down. Makes sense. What about the velocity? Positive or negative here? What do you say to that one, Chris?
I say it's positive because it's going up.
Yeah. Yep, exactly. So the positive because it's going up, I like it. Now, we have a positive velocity, we have negative acceleration, but be so careful. The acceleration is not negative because the speed is decreasing. Right? The acceleration is negative because of the direction of the acceleration, because of the direction of the force is a better way to think of it. All right. The first shall be last. What do you say? Jessica, what's the acceleration of the Rockito? Positive. You sound confident. It's going up, but isn't that the speed? I like it. I couldn't shake her. Right? Nice job. She's absolutely right. It's the speed is increasing upward, right? The truth, what's really going on here, yes, gravity pulls this thing down, but the rocket booster pushes it forward much, much more. Right? Otherwise, it wouldn't get to space. So it's accelerating upward, and since it's moving upward, the speed is also positive. Nice job. How you guys doing? Questions about those? Is that a question? All right. Here's 5 more. And these ones are more horizontal. These ones are probably a little trickier. Number 1, and this is all 1 right here. You have a dude driving down the road, sees a dog in front of him. Slams on the brakes. Here you have a muscular dude running with no clothes on. Kind of strange. Probably going to get in trouble for putting that online, but whatever. Here we have a ball rolling down a hill. Here we have a ball rolling up a hill. And here we have a ball rolling up a hill. Let's always use to the right, like we mentioned up here. Let's always use to the right as our positive direction. All right? Try these. Try them by yourselves for 2 minutes, and then we'll talk about them at our tables, and then we'll get together as a whole class of homies. All right, take a minute and check me here. See how I did. And I honestly just kind of threw those up there haphazardly. Maybe I even put some mistakes up there hoping you'd catch them. What do you think? Zach, what you got? Yeah.
The first one of the ball one, what if that's directly positive?
Well, let's see. What's our positive direction? Up the hill, right? Is the ball going to be forced up the hill? The ball is going to be forced down the hill, right? So the ball is forced in the negative direction. So I think the acceleration is going to be negative. Liam.
On the last one, I kind of think it's like, I'm not sure if this is right, but the Serena Williams one, that knows the ball of the hill, it's just going to come back down with gravity.
All right, this ball will eventually roll down the hill. That's good.
So with the acceleration be negative.
Well, here's the thing. On this problem, what did we say was our positive direction? We said down the hill is our positive direction, right? So the force on the ball is going to push it down the hill. That's why the acceleration is positive. Right. What else? I must have made some mistakes, right? I mean, this is me we're talking about. Working on it. All right, I don't feel like waiting for Zach all of a sudden. I'm going to keep going. I don't know why. I don't know. Something just came over me. Forget about him. Now, here is where we put it all together. All right, here's where we can use the equations that we've written. And this is a tough problem to start out with. So just kind of watch the general strategy. Watch what we do here. Whenever we get this type of problem, step 1 is, I highly recommend sketching. So the boy's up on a balcony, 30 meters. There's my sketch. Here's my boy. You're my boy, Blue. You're hanging out over the balcony with your go-go gadget arm. You're going to throw a ball up in the air. You guys know what I'm talking about? Did you ever see Inspector Gadget? Is that still around? Huh, all right, good. There's hope for the future. And the boy throws the ball up at a speed of 25 meters per second. 50 miles an hour. It's a pretty good throw. Could be. How long until the ball lands? And now, I know what you're thinking. I am actually standing here telling you that I taught you how to solve this problem. Kind of. I gave you the tools, even if I didn't train you in using them. So that's what it's going to be about. That's why I said we're going to be spending a few weeks learning how to use these tools. Here's the idea, though. Maybe you guys can answer a few intermediate questions for me, and we'll get there. Let's do this. Let's write down our equation. X, as a function of time, is equal to the initial position plus the initial velocity times the time plus 1/2 at squared. How many of these things do I know? Do I know the initial position? That's right, good. Now, before we say yes, 30 meters, let's be very careful. Where is my origin here? Where's my reference point? Because I'll bet if I just had you guys decide, half of you guys, about, would say, this is my starting point right here. I'm going to start where the ball starts. And the other half would say, I'm going to start at the bottom of the building, or the cliff, or whatever it is, the balcony. Right? Which one is the correct reference point? Or does it matter? It doesn't matter. You can use either one as your reference point. As long as you're consistent, you're going to get the right answer. All right? I'm going to choose this one. You probably want to too for now. All right? It's not that much tougher the other way. It's just, let's be on the same page. So this is my origin, and I'm going to say this is my positive x direction. So if all that's true, what is my initial position? That's right, I'm 30 meters above the ground, aren't I? Oh, the ball is. So 30 plus, what's my initial velocity? Do I know that? Good, it's in the problem. Initial speed of 25, so 25. Now, can I mess with your heads for a second? Positive or negative? The quick answer, be careful. Up is the positive direction. What direction is it moving? The initial velocity is up, right? Okay, so you're good. I'm just checking. Just want to make sure you weren't too hasty there. What about the acceleration? Do I know the acceleration? That's right. You know g. I'm going to do 10 meters per second squared times t squared. And I made a deadly error. Why is it negative? Gravity is going to force the ball downward. Right? So the acceleration is going to be negative. So here's where we're really doing applied math right now. This is Algebra 2, a fairly kind of middle-of-the-road Algebra 2 problem. But we have to actually use it and know how to use it. What else do I know? My question is how long until the ball lands. So what am I trying to find here? Time. I'm trying to solve this for t. Forgot a t right there, sorry. Do I know anything else? Do I know what the position is when it lands? Yeah. How high above the ground are you when you land? 0. All right? That's the point. So, again, that's where it's tough. It's definitely applied math. You have to know, 0. And then I'm trying to solve. 0 is equal to 30 plus 25t, I'm letting the units go, minus 5t squared. Quad solve. Yeah. Did I just hear a pouty sound? It's a quad solve. Come on now.
We can factor it first.
Yeah, let's try and factor it. The first thing, if you're going to try and divide, and I'm going to divide everything by -5. And I get 0 is equal to, let's see, t squared minus 5t minus 6. Q. Right, just divided everything by -5. Does this factor? Let's try it. I'm looking for two numbers that when I multiply them, they give me -6, and when I add them, they give me -5. Plus, let's see, when I multiply them, I get -6, and when I add them, I get -5, so I'm going to go plus 1 minus 6. It works!
So then what would that mean? Is that 2 is equal to positive 6?
Woohoo! So when I remember, we're not done. We have to figure out what t is. T is equal to -1 and positive 6. Go back to the problem. How long until the ball hits the ground? The ball hits the ground after -1 seconds. Does that make sense?
Yeah.
This is what we call a worthless solution. Extraneous solution. Has no physical meaning, right? Not really, anyway. But 6, a positive time, that does make sense, right? So yeah, Jessica's exactly right. The ball's going to take 6 seconds to hit the ground.
So then if you were supposedly to get like a positive x value, would that still just mean nothing? Or
Well, what you mean if you got 2 positive times?
yeah.
You would get 2 positive times if you were trying to figure out, say, if the physical situation dictated. So if I were trying to figure out when the ball was 10 meters above my head, I'd get 2 positive solutions.
And so that would be your answer with either what?
Yes.
Oh, because this, okay, yeah.
Once on the way up and once on the way down. For this one, there is only one physical solution. So mathematically, you're only going to get one physical solution. If you do it right, the math should always match the real world. Now, here's the deal, guys. We don't have time to work a bunch of different problems today. And that's probably